Hello, this is what time we're going to do Gibbs free energy, and Gibbs free energy is based upon delta S, which is entropy, and that delta S of entropy has to be calculated to do Gibbs free energy, and so please watch the video on entropy first if you have not done so already or know how to do entropy. All right? Please like and subscribe and share. I want to help as many people as possible, so please do. Now, Gibbs free energy is a feasibility of a process that depends on the entropy change and the temperature. Here's the entropy change, here's the temperature. So you'll have to calculate the entropy change, and it depends on the enthalpy change of the system, which is delta H. Now, this starts off from this reaction here. Energy released by a reaction, or the energy of a reaction essentially, is equal to the energy available to do work and the energy that causes the entropy change. So that's a T and that's a delta S. So basically we need to know the temperature and we need to know the entropy. And here is your delta G. Now delta G tells you whether your reaction is feasible or not, if it's equal to or less than 0. So let's have a look at it if we rearrange it. And this is the way you'll use it normally. Okay, and really important that you put everything in the same unit. So this is kilojoules, but when you calculate it in the exam, they'll make you do it in joules, so you have to convert it to kilojoules. Then the temperature, they'll normally give you degrees Celsius, so to convert degrees Celsius to Kelvin is plus 273. Enthalpy change is kilojoules per mole. Notice kilojoules, 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 kilojoules. Okay, and then you get free energy. Okay, which means your final unit will be kilojoules as well, because you've got kilojoules here and kilojoules here. Okay, right. Now, as I said, the reaction has to be spontaneous, and if it is, it will be delta G 0 or less than. Now, here's a reaction here where you've got hydrogen and oxygen. Hydrogen and oxygen don't react normally unless you add some energy in. Okay, so we know that this performed at 400. What is it feasible or not at 400 Kelvin? Now, 400 Kelvin is about 127 degrees. Okay, so if we raise the temperature of the vessel up to 127 degrees, would these two things just react and blow up? Okay, so really important in industry and things like that, knowing what temperature you can take something to before it just goes boom. Okay, right, so explain with the calculation whether the production of water is feasible at 400 Kelvin. So first of all, this is in joules. Okay, I need it in kilojoules in the end. Okay, so I'll convert it to kilojoules after I've calculated the delta S value. Let's put this to the side and let's calculate the delta S value. If you've done it before, this should be quite straightforward. Your products are minus the sum of your reactants. So sum of your products minus the sum of your reactants. You then read it off the board here. You look at the equation, read the numbers off, okay, and then you use the balanced equation to do it as well. So there's 2 times your water, and this is 2 times your hydrogen. Okay, so it's products minus reactants. You get that as joules per Kelvin per mole. Notice it's in joules. Okay, which means we need to convert it in here to kilojoules. I generally take this number, times it by this number, and then minus that away from 484. And I'll talk about more about that later. So basically, when you put that into your calculator, you need to make sure that everything is in the same unit. So this is in kilojoules because I've got it from here. And this one is this number here divided by 1,000 to turn it into kilojoules. You put that in and you've got 519.6 kilojoules per mole. Okay, well that is a positive number, so this reaction is not feasible at 400 K. It's above 0. Okay, so not a feasible reaction. As it's above 0, not feasible. Okay, now just remember, convert the entropy to kilojoules before you do the calculation. Really, really important. That's where the mistakes happen. Really important point. Now, for the reaction to be spontaneous, delta G has to be less than or equal to 0. So if we want to know when something is spontaneous, determine the temperature at which it is feasible, okay, we just set the delta G to 0 because that's the point at which it becomes feasible. It's rearranged to this. Now, I'm going to describe this to you as if you're not a mathematician, because I'm not, okay? If delta G is equal to 0, it looks like that. If it looks like that, that means if I add minus T delta S to the other side, I'll get T delta S equals delta H. If I then divide by delta S, I get delta H divided by delta S. Now, in the exam style video, exam style question, we'll do a question like this so you can fit it in, but we're not going to do one for now. But basically all you do is you put in the number for delta H, you put in the number for delta S, and they have to be the same unit again. So they have to be in kilojoules, each of them. And then you'll find out your temperature. Right, okay, so once we found out whether the temperature is feasible, that's one type of question. We can work out delta G, which is another type of question. We then have to look at the feasibility of reactions depending on the equation itself. So what does that mean? What it means is, here's the equation. And I think it's more helpful to think of this as having brackets around it. And that's why I put the brackets in there. And I do that in the calculator anyway. I times this by this and then minus it away. Okay? Now, you're going to be given values in the exam and be asked to say, do you think this reaction would be feasible or not? Okay, but they won't necessarily ask you to calculate it. So they might not give you numbers. They might say it's a positive entropy change or a negative entropy change, or this is a positive delta H or a negative. They might not tell you. So how can you answer whether the reaction is going to be feasible or not? So here we go. First of all, if this is positive, I need you to put this into your brain and just say, right, okay, that's a positive number. And that number is high, okay? Sorry, high. So this T is high. If you think of it with the brackets around it, I think it's easier. A high number times a positive, which means this is going to be a very large positive number. So a positive number minus a very large positive number. That means delta G is likely to be a negative number, because if you take a big positive number away from a positive number, you're more likely to be negative. So at high temperatures, this is more likely to be negative. So this is likely to be a spontaneous system. If we do the next one and we say, right, delta H is negative and delta S is negative, but it's low, the temperature. The temperature is low. So again, in our non-mathematical, mathematical brain, depending on what you've got, a low number times a negative, which means I'm going to have a negative number, but it's not going to be a very low negative number, okay? Okay, it's going to be like, for example, minus 10, minus 20 instead of minus 400. It's going to be quite small. If that, so basically, well, the magnitude of it's going to be small. So minus, magnitude y is a small number. So minus is a plus. So we're taking a minus and adding a small number to it. If that's the case, that's likely to be negative, because it's not likely to take it over 0, because you need a bigger number to take it over. So at low temperatures, this looks like it's going to be feasible. We then go to a negative, okay, and then all temperatures, any temperature whatsoever, and a positive. I want you to sit and think to yourself, what does that mean? Okay, stop the video and try and think. And do that with the next two. So any temperature times a plus. That's going to be a positive number of some sort. Okay, that'd be a minus a positive number. Well, that means a minus a positive number is going to send that more negative. Okay, which means that's going to be spontaneous. Last one, a positive and a negative. At all temperatures, a plus, minus, a minus. So a plus, minus, a minus. Minus and minus is a plus, so it's a plus plus a number. Well, a plus plus a number is always going to be positive, which means that's not feasible at all at any point. So I've given you 4 options. Okay, so 4 options for you to think about. So if we put this in what you might get in an exam in terms of an MCQ, here's what it might be. So I'd like you to stop the video and just go down each one and say, what do you think this is going to be? So the question asks you, which row has signs for delta H and delta S for a reaction that is feasible at low temperatures but not high? Okay, so let's put this to the side. Okay, delta G here, we've got our thing, we've got our brackets, right? Okay, so let's think about, we want a negative delta G. Okay, it says on the first one, negative, negative. So is that going to be a negative delta G? How do we get that to be a negative delta G? So that's a negative minus a minus. which means I want this to be a small number, okay? Because a minus is a plus. So I want this to be a small number. So this would be a negative number if that was a low temperature. If, though, this was at a high temperature, that would be a minus, so it would be a plus. So this negative value would be plus, and it would be a large number, which means it wouldn't be feasible if this was at high temperatures. Okay? So if that is the case and that's not feasible at high temperatures, the answer is definitely A. It is feasible at low, but not at high. Okay? So it's really, really important that you can do that. It's normally a 2 or 3 mark question. Okay? So just think about the magnitudes of these things and you have to describe it in terms of the magnitude of T delta S. So you have to say, okay, the T delta S would have a high magnitude or be a large number and therefore blah, 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 blah. Okay? Right. Minimum and maximum temperatures. Now, this is a very useful graphic which I'm going to show you. So we have arrows going in this direction. It all makes sense in a minute. Okay? Now, and this kind of tells you your value. So if you have a positive delta H and a positive delta S, okay, your delta G, as the temperature gets higher, can you see the temperature gets higher? Your delta G is likely to become more negative and therefore feasible. If you have a minus delta H and a plus delta H and a minus delta S, as the temperature goes up, it becomes more unfeasible. Okay? Now you can think of it like this and you can do a graph, or you can just do what I did in the previous slide. Okay? Let's go for the next one. So it's a minus delta H and a positive delta S. As the temperature goes up, it's going to become more feasible. And if you've got a minus delta H and a minus delta S, as the temperature goes up, it's going to become less feasible. Okay, and this gives you your kind of rules. So your rules are delta H and minus delta S. Delta G becomes more positive as temperature increases. Okay, and that'll have a maximum temperature. So delta G becomes more positive as the temperature increases. So there's a maximum temperature at which it will be feasible. Okay. Next one, delta G becomes more negative as temperature increases. So what we've done is take this graph, okay, and club them together and put them together. As delta G becomes more negative as temperature increases, that means you'll need a minimum temperature. So it becomes more negative as temperature increases. So basically, as the temperature increases, it's more negative. So basically, there'll be a minimum temperature at which it works, okay, because we said as the temperature goes up, it works more. So there'll be a temperature at which it starts to work, and then as the temperature goes up, it starts to work more. So let me just go with this. This is quite complicated in your head. Remember, on this graph, these two work the same. These pairings work the same. Delta G becomes more positive as temperature increases. So as temperature increases, it becomes less feasible. So there'll be a maximum temperature at which it can work. After that temperature, it would not be feasible. This one becomes more negative, therefore more feasible as the temperature increases. So I have the opposite, a minimum temperature. Okay, a minimum temperature at which it works. Okay, and that is how you do the 2 delta G. Now, do not worry too much about this. This is about going into it graphically, and it's quite a nice little graphic that does. You can still just work it out manually by having the graph and just saying, what's the minus times the minus and things like that. Okay, so the other way, if the other way works for you, great. If this way works for you and you just like remembering it by rote, this works. If you want to go the other way and just do it as you're given with the magnitude of the 2 numbers, please do that as well. Now this is the end of the delta G video, which is based upon the basics of delta G. The next one will be the exam style questions. Please like and share, more importantly share, and subscribe. Thanks very much.